All right, so we're lucky to have Kabir today. He's going to talk about this exciting line of work on minimal assumptions for quantum cryptography. So without further much ado, you can take over.
Sure. Thank you. Hi everyone, I'm Kabir from UIUC, and I'll be talking about our recent work, cryptography from quantum One-Wayness, which is joint work with Dakshita Khurana from UIUC. So I start by stating one of, if not the most important problem in cryptography, which is, does secure cryptography exist? And if it does exist, how do we know that it exists? And we ask this because modern cryptography began with schemes like Diffie-Hellman RSA, which were also the first schemes that were proven secure. And here, proven secure means that their security was based on assuming that certain number theoretic problems were hard. And the problem when you build schemes this way, by assuming that some particular problem is hard, is, well, what if that problem turns out to not be hard? And in that case, your cryptography breaks down. Does it even exist? And this problem of, okay, we have all these different assumptions, it leads to the natural goal, which is the holy grail of theoretical cryptography, which is we want to base cryptography on the weakest possible complexity assumptions. And we want complexity assumptions because they tend to be weaker, and they're generic assumptions that can be instantiated from a variety of these different concrete problems. So in the classical setting, the minimal assumption for cryptography is known, which is to say there is a simple complexity assumption called a one-way function, which is necessary for all classical cryptography. And what is a one-way function? It is a function that you can compute efficiently. However, for a randomly sampled y, it is hard to find an inverse of y under that function. It is computationally infeasible. Now that's for in the classical setting. Once you start adding quantum computation to the mix, things are a bit different. That is because you can relax or even remove some assumptions using quantum resources. For example, the famous example is quantum key distribution, which is possible without making any assumptions. However, many central cryptographic primitives like bit commitments and multiparty computation, these require some kind of computational hardness assumption. However, recent work has shown that these can be based on assumptions that are potentially weaker than one-way functions. So the picture looks something like, for classical cryptography, there are one-way functions, which are the central primitive, equivalent to a lot of cryptography, and implied by all classical cryptography. What is that? Can I remove this? However, there are some quantum cryptographic primitives which are implied by one-way functions. But crucially, one-way functions do not seem to be necessary for their existence. And in fact, we can say something even stronger, which is, suppose p is equal to np. One-way functions don't exist, commitments don't exist, all classical cryptography breaks down. However, it is plausible that some of these quantum cryptographic primitives remain secure. So if there's nothing else you take away from this talk, this is why you should be excited about this whole line of research. Cryptography potentially even in algorithmica. That is the promise at the end. Let's see if we can achieve. So in this setting of cryptography without one-way functions, there is this natural open problem that what now is the new minimal assumption that is required for quantum cryptography. And so far there have been two major candidates for the minimal assumption. One is called one-way states, and this captures in some sense average case hardness of search problems. And the other assumption is something called EFI pairs, which captures the average case hardness of distinguishing or decision problems. Now,
how about non-clonable states?
How about unclonable states? So those kind of seem to be leading in directions that are entirely separate from these classical cryptographic primitives. Like when we say cryptography, we are talking about things like commitments, multi-party computation, encryption, while unclonability seems like it's something additional, like it doesn't fit very neatly into all of this. And people are trying to join them, like I think.
It's more like non-malleability, right?
Yes, non-malleable. So imagine a non-malleable commitment where the non-malleability was coming from unclonability, but you still need normal cryptography for the commitment part. So if you don't assume any classical cryptography, or if you don't assume one-way functions, then I guess they're not very well, it's not very well known how they connect. And it is an open problem, and trying to get unclonable cryptography also unified with this work. So I think the one big thing is from mini schemes getting commitments, I think would start unifying things like this. Anyway, maybe you can talk about that offline. So a quick reminder about what a one-way function is. It is a function that takes a uniformly random string x and maps it to f of x, where f, the function, is efficient to compute. And the security property is that it is computationally infeasible to invert given f of x. Hard to find x prime such that f of x is equal to f of x prime. Formally, for all efficient algorithms that take input f of x and output x prime, probability that the match is negligible. This should be familiar to many people. Now what a one-way state generator is you can think of it as a quantum analog of a one-way function, which is we want this hard to invert property where we'll just make our output quantum. And the natural way of doing that is we say there is some key generation process that allows you to sample a random classical key, where k is this classical string. And then there is a state generation process which maps this key to a quantum state phi of k. And here we want similar properties, generation of key, state generation, these are efficient. And we want it to be computationally infeasible to invert, which is to say, given phi k, or maybe even many copies of phi k, this tensor T refers to many copies. We can, it should be hard to find some k prime such that phi for k and phi for k prime have some overlap. Formally, what overlap means is we want the expectation of the overlap for any efficient algorithm that takes in t copies of phi k and outputs k prime. We want the expected overlap to be negligible. So in some sense, it measures how close your answer was to the correct answer. Now, if one-way state generators are the analog of one-way.
I'll ask some questions about this. So you're not asking the algorithm to find the k exactly.
Yes. So one reason for that is, suppose for a one-way function, you could have many keys that map to the same output, in which case it is unreasonable to expect any algorithm to find exactly which key you're thinking of. You just need to find some key that is good enough.
Why we need the tester? So
why do we need it? Why is just not one copy enough? If you just have one copy, it can be like information theoretically secure. So turns out that if I give you one copy, it can simply be impossible for you to find an inverse. It could be completely hiding. So we need, or rather we allow our adversary to get many copies. It's a stronger definition of security, that even if you get many copies, you should not be able to break it. And if we want to build any useful cryptography from this one-wayness thing, we want it to be secure even when we are given many copies.
What's a typical conservative T and aggressive T?
Okay, T is unbounded polynomial. The adversary gets to tell you how many copies it wants, and it gets as many as it wants. It is in fact only polynomial because the adversary is efficient. So,
but we could define one-way state generators with for fixed T.
Exactly, you could. So I believe less than order n by log n, where n is the length of the key, is information theoretically possible. And for our construction, we just need it to be order n secure. And there's been work narrowing these both to get to some information theoretically secure, so useless, and useful, and as low as possible number of copies. Right. So that was one-way state generators. If you have any more questions, feel free to ask. Sure. So next we go to EFI pairs, and one-way state generators analog of one-way functions. Then EFI pairs are the quantum analog of commitments, and commitments stripped to their barest essentials. And what an EFI pair is, it is nothing but a pair of two efficiently sampleable mixed states, rho 0 and rho 1. And a mixed state is, you can think of it as simply a distribution over quantum states. So two distributions over quantum states. Such that both of these distributions are statistically far. However, they are computationally indistinguishable, which is to say for any efficient algorithm A, and if you're given a random sample from one of these distributions, you cannot tell which distribution it was with better than negligible advantage. So although they are statistically far, we need them to be statistically far for this definition to be meaningful. They're still computationally indistinguishable. And EFI pairs, the name might seem a bit, where did it come from? E stands for efficient, F stands for far, I stands for indistinguishable. So those are the three properties. Those are the three properties I would like you to keep in mind.
So this on one copy implies many copy already for this. Because these are publicly sampleable.
Yes, basically. Right, because yeah. These are the three properties I would like you to keep in mind as we go on. We'll be trying to achieve all three properties simultaneously. Efficient, statistically far, computationally indistinguishable.
One question?
Yes.
So you allow row 0, 0, 1 to be mixed states. So they can be
Yes.
even entangled with each other or some like residual state.
So row 0 has to be a self-contained defined mixed state. And row 1 has to be self-defined contained mixed states. Both of them have to be publicly sampleable. So I should give you a bit B and you output row B.
It's like the distribution of commitment of bit B. Rho B is the distribution of states for a commitment of B.
Also, it's something like, for example, I can sample like many row 0 copies.
Yeah, you can
by myself.
Yeah, you can compute as many of them as you want.
Yeah, and those copies should not be like mutually entangled.
I mean, by definition, they would not be, because if you can keep sampling more and more, like how do you? Okay, row 0 is. There is an algorithm which, given a bit B, outputs a mixed state. That mixed state is defined as row 0, as row B. So there's an algorithm which you give it 0, it outputs row 0, give it 1, outputs row 1. Whatever it outputs, you define as row 1. So if you run it again and again on different registers, you get different row 0s, and by definition, they would be unentangled because they're all on the start of unentangled on different registers. If that makes sense. I think the way to think about it is just distribution over mixed states, and we don't care so much about the entangled part, just that they're efficiently generatable. So I will situate these primitives in their context by showing how they relate to the broader landscape of quantum cryptography, at least some of the landscape. Which is to say, most quantum crypto primitives end up implying one or the other of these objects, which is quantum many variants, digital signatures with some caveats, imply one-way state generators, pseudorandom states, one-way functions imply both of these objects, and EFI pairs are in fact known to be equivalent to secure multiparty computation in the quantum setting, zero knowledge for NP, QMA, and just quantum commitments. So EFI pairs seem to be the more usable object because we know these equivalences, while one-way state generators are perhaps less understood. But the main thing that was unknown about this is what is the relationship between these two objects. Specifically, their equivalents in the classical world, in the classical setting, which is to say one-way functions and commitments, are known to be equivalent. With one-way functions, you build commitments, you can build one-way functions. However, in the quantum setting, there are many barriers to showing this kind of equivalence. And in our work, we overcome some of these barriers by showing that you can build EFI pairs from one-way state generators, with the caveat that the one-way state generators must have pure state outputs, which means that for a given key, it maps to one quantum state and does not map to a mixture or a distribution over quantum states. So the key to quantum state map.
With pure outputs means this assumption is weaker or stronger?
A general one-way state generator could have mixed state outputs as well. So if one-way state generators with pure state outputs is a stronger assumption. We are adding more restrictions on what our object has to be. the consequences of this result are most things start and end up implying one n-way.
Can you give an example of how a mixed state, like what process gives you a mixed state? Like,
What process gives
like
you a mixed
which-
state?
I mean, when I think about algorithms,
Yeah.
I would typically think about something out being a pure state.
Right.
What kind of,
Maybe you can think of, I don't know if I'm still on camera, maybe I'll write it over there. You can think of some algorithm that takes in a key. Takes in a key k and outputs like some public phi or some state phi entangled with some junk. And maybe given the junk you can find, given junk and phi you can find k. But if I trace out the junk, remove the junk, then this is left as some mixture over phi. Then it is hard to find k. And if by purifying it becomes the hardness goes away. The hardness has to do with the mixture in some way.
So when you say pure output, it includes the junk part.
No, like the here where we had junk, if the junk is revealing information about k, and for security to hold we have to give phi, then we will have to remove junk. I guess saying entangled is wrong. It should be, sorry, saying tensored is wrong. It should be like entangled junk. Yes, phi output and junk. But you need to trace out the junk for it to have some kind of hardness. And if you don't trace out the junk, then it is easy to find k. So for a pure state output, we want that even when you trace out the junk, it should remain pure, which is to say the output should look something like this.
So the right way to think about this is that, let's say I draw several copies.
Yeah.
And then I define a projector around, let's say, the first state. Every time I sample a copy, it's going to project to the same, it's going to be one. It's always going to be equal.
That, yes, you can think about pure state outputs as, yeah, you given one state, every time you run your one-way state generator on the same k, you get exactly the same state, which means you can project onto the same state and get the
If it's
same.
a mixture, there's a chance if you're not.
If you get a mixture, every time you'll get a random output. So here's an example of a one-way mixed state, one-way state generator. It's not verifiable, but commitment to x, just a classical commitment to x. This is phi x or rho x. So because the output of commitment to x is not some fixed value. If it was fixed, it would not be hiding. It is some distribution over values. And here, it is essential that it is a distribution if we want to hide x. But it does have one-wayness, which is I give you a commitment over x, which will involve some randomness. Then it will not be the same commitment every time. It will be random, but still hides x. This is a classical commitment, maybe. This is not part of the input. This is just randomness that we insert. Does that clear things up? Sure.
And the other side is not known.
The other side is not known yet. You can do some like fairly simple things by saying, okay, a commitment is technically one way. You can't check what the value is. You can't. I can't give out the key for a quantum commitment necessarily, but you can say one-way state generators with inefficient verification. But essentially, it is not known. What we want is efficient verification.
Sanity check. So if you only focus on a generator with pure outputs,
Yes.
could you go to the definition, the one-way state generator? Does that mean the value of the right-hand side should just be 0?
Right hand side.
The adversary should not output a k prime such that the inner product.
Not necessarily, because you could have if you think of phi k as a state, I'm just going to erase this.
Oh, maybe because the output is pure state, but not necessarily orthogonal.
Yeah, exactly. They're not orthogonal, and that is the big problem that we face here.
You you don't require the output to be orthogonal.
If
I
the
see,
output
I see.
was orthogonal, we could just kind of imagine that it's a classical state just rotated in some basis. As classical string rotated in some basis.
Then that would be exactly equal to one-way function.
Yeah, if you knew what the basis is, which you might not, but it won't be equal, it would behave very similarly. I think a lot of the problems would go away.
I see.
Classical technique should simply apply in that case, if they're all just completely orthogonal. Right. Yeah, so result is everything ends up, lots of stuff ends up implying EFI pairs, which means that it's pretty good evidence that EFI pairs are some minimal assumption in quantum cryptography. This doesn't unify everything, so it's not like the problem is resolved, but it is showing connections, that things are, EFI pairs have some kind of very weak hardness.
Why EFI pairs imply commitment but not imply one function?
Okay.
It has a
Okay,
commitment
perhaps I should have clarified this. All of these are quantum objects.
Okay.
EFI pairs imply quantum commitments, they imply quantum zero knowledge, quantum MPC,
Okay.
and one-way functions are the classical object. Yeah, good catch, I should change that. So, our results are, we can split them into two theorems. First, we show that pure one-way state generators imply a simple object which has classical inputs and classical outputs. And this object is referred to in prior literature as one-way puzzles, and we believe that this object is interesting in its own right, and I will say some things about it. And the second part is we show, using a mix of some quantum and classical techniques, how to use one-way puzzles to build EFI pairs or quantum commitments that are equivalent. Now, just for warm-up, let's talk about how you do this in the classical world. Suppose you start with injective one-way functions and you want to build EFI. And by EFI, you want two distributions that are efficient to sample from, statistically far, and computationally indistinguishable. Now, the Goldreich-Levin theorem gives a simple hash function such that this distribution, f of x, comma, Goldreich-Levin hash of x, is computationally indistinguishable from f of x, comma, just a random bit. And what that means is, if we have that be our first distribution, f of x, comma, random be our second distribution, we have two distributions that are computationally indistinguishable. So we have the I. They are statistically far because f of x being injective, f of x fixes a particular single x, and which means that the hash of that x is also fixed. While in the second distribution, that hash bit can be something completely random. So these two distributions are far. I will pause here if anyone wants to ask questions. This is the base ingredient through which all such constructions proceed. Now, this is if you have injective one-way functions. You get efficient, both of them are efficient, statistically far, computationally indistinguishable. Now, what if our one-way function is not injective? Then the problem in that case, we still have two distributions that are computationally indistinguishable, but they may not be statistically far. That is because, given f of x, that does not fix precisely which x is being used here, which means there could be many possible pre-images of f of x. And in general, that means that this Goldreich-Levin hash of x is not fixed, and maybe, in fact, close to uniform. So the distributions are not necessarily far, they may in fact be identical, because f of x leaves some ambiguity in the pre-images. And the core idea in Hastad, Impagliazzo, Levy-Lubin is, sure, we know how to use injective one-way functions, we don't know how to use regular normal one-way functions. So can we construct an injective one-way function using f? And the answer is no, we cannot. But can we construct a one-way function that is as good as injective? Injective most of the time. And the tool that we'll be using here to try to get something that is close to injective is something called pairwise independent hash functions, which are these simple hash functions known without any assumptions, information theoretically, which take in some order n bit seed and n bit input, map them to an L bit output, with the property that for any x1 and x2, the probability that our hash maps both of them to the same point is like 1 over size of the output. So they might as well be sampled independently when it comes to whether or not they collide. And this is a well-known tool. No hardness assumptions required here. I will abuse the notation slightly to use small h to refer to both the function and the key for that function. This is standard practice. And the idea is we want to eliminate the ambiguity in preimages. Given f of x has one preimage x, but it could also have many other preimages, x1 prime, x2 prime, x3 prime. And we want to in some way fix a single preimage out of all of those preimages. And the idea is we can do this by appending the hash of x to f of x. And if we choose this, the length of this hash very carefully, we can make it so that it's very unlikely that any of these x's, x1 prime, x2 prime, x3 prime, and x, that they collide under this hash, that they collide under h as well. So these preimages collide under the function, but they do not collide under the hash additionally, because you have leaked more information about x, and this helps, makes it less ambiguous which x you're talking about.
But if there are like many preimages,
Okay, you hash more and more. So
but then you leak more and more.
yes, and that is what I'll talk about next, which is that the length of this hash is very crucial and needs to be tuned very carefully. Because if you hash too little, like say you have lots of preimages, and your hash output is a single bit, this single bit will not help you disambiguate very much. You have like a million preimages in one bit, how will you decide which preimage is being chosen? But if you hash too much, if you hash like more than the length of the input, say, then you are leaking a lot of information, and it is unclear that whether your object is still hiding x at all. In fact, if you hash too much, it is not one way. One-wayness breaks down. So it needs to be carefully chosen so that it's long enough to disambiguate, but not so long that it loses hiding. And the value that you need to hash is roughly close to the log of the number of preimages of f of x, which I will represent as size of f inverse f of x. So we need to know how many preimages f of x has and hash to the log of that much. So just enough to fix roughly one preimage on average. So what we are going to do with this technique is we can now get a one-way function which is close to injective if we know how many preimages it has. So we start with f of x, h of x instead of just f of x. And then we get these two distributions where they are computationally indistinguishable by the Goldreich-Levin hash function. And they are statistically far because f of x, h of x fixes a single x with a good enough probability, such that the Goldreich-Levin hash of x is fixed in the first distribution and it is just a random bit in the second distribution. So we get far, we get indistinguishable. The problem is, in general, the number of preimages of f of x is not efficiently computable. So the construction is not yet efficient. However, that is something that will be dealt with later. We get far and indistinguishable. And the crucial thing to even start off is that the length of this hash depends on the exact number of preimages of f of x. And this represents something of a problem, because suppose we try to instantiate this approach using our quantum analog of one-way functions. We are just going to replace the output with phi of x. That is the natural thing to try. So suppose we start off with an injective one-way state generator, then phi of x, h of x is computationally indistinguishable from phi of x random bit. And because they're injective, phi of x fixes a single x, everything goes through. When you start to remove injectivity, then we start needing to append the hash of x. And the length of this hash will, as before, depend on the number of preimages of phi of x. And okay, is everyone clear with this, that this we depend on the number of preimages of phi of x? Any questions? Okay.
What does injectivity mean here in this quantum?
Given phi of x, it fixes an x. This is a bit
This
vague.
one copy fixes an x.
One copy, however many copies you want to use there. Say one copy. It's, the injective construction is not super interesting. It just works.
When you say the preimage of a quantity, why is the preimage of a quantity?
Exactly. What is the pre-image of a quantum state? Because quantum states can overlap, which is we can think of a quantum state as a vector where a single qubit can be a value 0, can be a value 1, but it can also be in superposition states, which are like a superposition over both 0 and 1, which is something like the plus state. And the problem when you have overlaps is, in general, 0 and plus, which is a state which overlaps with 0, these cannot be perfectly distinguished. And if there's any test you have that checks, okay, whether I have a 0 or not, the plus state will also pass that test with some probability. So fundamentally, these quantum states have some, plus shares some properties of 0. You cannot completely distinguish them. The reason this is a problem is when we start defining what a pre-image of a quantum state even is. Now, consider the following setting. You have two strings x1 and x2, and they map to one-way state generator outputs phi of x1 and phi of x2, where these phi of x1 and phi of x2 have some overlap. They're not the same, but they're not completely orthogonal as well. There's some overlap. So the question is the string x1 a pre-image of phi of x2? Suppose you say that no, it is not. We can just simply disregard it. Well, if you give an adversary phi of x2 and it outputs x1 as a candidate pre-image, it would still pass verification with some probability, because phi of x1 has some overlap with phi of x2. You cannot perfectly distinguish them. So if x1 was passing verification for phi of x1, it will still pass verification for phi of x2 with some probability. An adversary that given phi of x2 outputs x1 is still breaking one-wayness in some way. So okay, then maybe x1 is a pre-image. It allows you to break one-wayness, so why not just call it a pre-image? Well, x1 does not exactly map to phi of x2, it maps to phi of x1. And although you cannot distinguish them perfectly, you can still distinguish them with some probability. If I give you phi of x1 and tell you, hey, x1 is a pre-image, you can check, if I give you phi of x2 and say, hey, x1 is a pre-image, you can notice that I've given you the wrong pre-image. So you cannot simply say that x1 is a pre-image, you cannot say that it's not a pre-image. It's ambiguous. Well, so we want to get rid of this problem of overlaps. And one natural approach of getting rid of overlaps is if you take many copies of these quantum states, their overlaps go smaller and smaller, and eventually you can make them orthogonal, which is what we want. So suppose we fix some polynomial t, we take t copies of each of these states, and that makes them orthogonal. Well, the problem with doing that is we have taken these two states which had some small overlap and made them orthogonal. But this same process of taking t copies, if you started with two states that are actually really close enough that you can kind of consider them the same state, after taking t copies, you might end up in a situation where the t copy versions now have some overlap. So you got rid of some overlaps, but you produce more overlaps. So you cannot a priori fix some polynomial that gets rid of all possible overlaps. In fact, you can construct some contrived state generators where no matter what polynomial you choose, there will always be some kind of overlap. So like just repeating in parallel doesn't seem to work. So here is another idea. This whole problem of what is a pre-image is happening because quantum states have overlaps. And note that classical strings don't have this problem. Two classical strings are either the same string or they're just different strings. You will never confuse one for the other. They're either identical or orthogonal, no partial overlaps. So what if we could convert this one-way state generator output into some kind of classical string? You could obtain a one-way object with classical outputs. And the natural approach is you take your quantum state and you try to write down some classical description of this quantum state. And the task of writing down a classical description for a quantum state is exactly the task of quantum tomography, which is you get a bunch of copies of a state and you want to write down some classical description of what this state is. So you can simply write it down. You don't have to deal with vectors and overlaps. It's just a string. The problem is that any classical, so the problem is that the size of this description is necessarily exponential. In general, n-qubit states do not have polynomial size classical descriptions. You cannot hope to get a simple string that contains all of the information of phi. So what this means is if you try to output a classical string that is a description of phi, you will have to throw away some information, and a lot of information in fact. So what if in doing this process of distilling it to a classical string, the information you throw away contains the computational hardness. Like what if you're throwing away the wrong information? So we don't, it is not clear whether your object remains one way or not. So the solution that we show for this problem is using a technique called efficient shadow tomography, which is a scary word, but I will break it down. What efficient shadow tomography means is you take some copies of quantum state phi, and you compute a classical description of this state phi, which is polynomial sized, can be computed efficiently, but it loses a lot of information about phi. The classical description S, which is called a shadow, it loses a lot of information, but it can be used to estimate some limited set of properties of phi. And it turns out that the properties that we can estimate using S are precisely the properties we want to conserve. Specifically, what shadow tomography does is it takes phi, many copies of phi, psi, I've been saying phi. Psi, it takes many copies of psi, maps it to a classical string S, which is the shadow S, and it comes along with an estimation procedure, which given the shadow for a state phi, can estimate the overlap between phi of k and psi for any k. So given a state, you compute the shadows, you lose a lot of information, but you can still compute what overlaps this state had with other states that you choose. This estimation procedure is not efficient, but we will see that it turns out to not matter. Formally, with high probability over the sampling of this shadow, for small constant epsilon greater than 0, so this is our small error, the estimate of the overlap is epsilon close to the actual overlap. So given the shadows for a state, we can compute its overlap with other states, up to some small error.
Question?
Yes.
So when we apply that shadow, do we need to fix what property we want?
No.
So that shadow is like a universal
Yes.
property.
Okay, like some class of properties you have to, there are different types of shadow tomography. There's a type of shadow tomography which is good for our thing, but we don't need to know exactly what those properties are.
I guess my concern is, if you don't need to fix the property beforehand, then that means S contains all the information of psi.
No, because just given estimate, just the ability to compute these overlaps for small constant with small epsilon error doesn't really allow you to compute the state itself. So you can think of that state as containing an exponential amount of information. So you can't actually condense it into this shadow string.
By the way, this is, if I generate a state adversarially,
Yes.
then I can fool the shadow, right? Like I can come up with a state which may be like close to 5k, but our shadow predicts that it's not. I'm just asking, is it like...
No, not...
Because
no,
of course you're losing a lot of information, so...
Yes. So the way this shadow tomography works is you can think of it as applying random measurements in random bases.
Yeah, so then if it's like random projections, then clearly you should be able to fool it.
I guess the hope here is
Yeah, you don't know the projections ahead of time. The shadows procedure will sample them.
I see.
So if you knew
know
which
the
projections,
then you can.
yes, probably. I'm not sure, but it seems very plausible. But the whole idea is that you don't know the projections ahead of time. So shadows preserve overlaps is the idea.
even the adversary knows the projection ahead of time. As long as the psi it is in the product state, that means we have many copies of psi.
Yeah.
I still be fine.
If the adversary knows the projections ahead of time.
I'm not really sure.
And this is just reminding me of sketching. Like when sketching, obviously you can come up with instances where you can fool the sketch completely. It's just a random low-dimensional projection, right? So you can always fool, come up with ways which like you can always fool it. At least classically, and maybe I think this should also be true quantum.
Because I'm thinking that so the formal statement is that with high probability over S, okay, yeah, I guess it depends on whether the statement holds for all psi, and yeah, I'm not sure.
This holds for all psi.
If it holds for a side, then it also holds for the adversary chosen side.
Well, it holds for all psi with over the
Overlap
probability
probability.
of the shadows. So there is some
Fix the
probability
psi,
that
and then when you choose the shadow, then it's correct. But if you first sample the shadow and then choose the state, looking at the projections, then you can do it.
Oh, I see.
so there's a chance of getting a bad shadow, and if you know what those measurements are, maybe you can make it always produce a bad shadow. But if you give the state first and then the projections are chosen randomly, you can't do it. So the idea is we are going to replace our quantum state with these classical shadows, and instead of phi of x, we're going to use the shadow of x. The output will become classical while, and I'll show this, inversion remains computationally infeasible, for some definition of inversion. And we define the one-way puzzle object to formalize the properties that we get when we do this. And what is a one-way puzzle? A one-way puzzle, you can think of it as a sampler for hard problems along with their solutions. So you have some process gen which samples hard problems along with their solutions, where given a problem and a solution, you may not necessarily be able to efficiently check that the solution is a valid solution. So you have a generator which samples key k, and these classical string k, classical string p, where k I will call the key and p I will call the puzzle. And the puzzle is in some sense talking about some hard problem, and k is the solution to the hard problem. And the computational property we require is, given such a sampled puzzle, it is hard to find a valid solution or a valid key k for that puzzle. And validity does not need to be efficiently checkable, it must be defined. So there may be some potentially unbounded time verifier, which given a key in a puzzle is able to check whether this is a valid key or not. So honestly sampled keys and puzzles will always verify with high probability, but given p, it is hard to find some key k prime which verifies.
So is it fully determined by a classical scheme?
Is it fully, sorry?
So sorry, is there a fully classical scheme?
No, so yes. So the inputs and outputs are classic. However, this generator crucially must be quantum. Or rather, if you're going to use this in our construction, it must be quantum, because suppose the generator was strictly classical. Then we could think of this generator as taking some classical randomness string r, where r is just uniform, and given r, it always produces the same output. In which case, you could think of r as the key of a one-way function, and the output as the output p as like the f of x for that one-way function. So one-way puzzles are actually become equivalent to one-way functions. It's not like, the gist is, if generator is classical, in the classical setting, one-way puzzles are equivalent to one-way functions, and which is why they're not talked about much in the classical setting. In the quantum setting, precisely because for a quantum algorithm, you cannot pull out all the randomness and just say, for this string, for this randomness, it produces this output. The output is fundamentally random. Because of that, we can build interesting objects from this hardness assumption. And because remember, these things all have to exist even if p is equal to np. So if this was equivalent to one-way function, it would simply break. Anyway, right. Honestly sampled key and puzzle will verify with high probability, and it is computationally infeasible to find a puzzle that a key for a randomly sampled puzzle.
So the K and P is quantum state or classical description?
Sorry?
The K and P.
These are strings, classical strings. Classical inputs, classical outputs. Algorithms themselves are quantum. So I will show how we build one-way puzzles from one-way state generators, quickly using the shadows process. So to produce a key and a puzzle, we just sample a one-way state generator key, and we use that key to generate quantum state phi k, generate shadows s of k. And the idea is that given shadows, it should be computationally hard to find a valid key that produces that shadow. So we output k and the shadow k, and the shadow is the puzzle. And to verify, the unbounded time verification process is just given a candidate key k prime and a shadow, just estimate whether the state for k prime overlaps with the shadow, with the state for which you've taken the shadow. Remember that this estimator process is estimating this overlap up to epsilon additive error. So so suppose that you had an algorithm which, given shadows for k, outputs k prime that pass verification, which is to say it outputs k prime such that the estimated overlap is high. If the estimated overlap is high, then the actual real overlap will also be high by the correctness of our shadow procedure. And because the actual overlap is high, that means that this k would also break the one-way state generator.
So it's hard to break the shadow even
Yes.
if we know the shadow.
Yes.
When we take the k prime, even if we know the shadow, we still cannot give a k prime so that they are close.
Yes, exactly. And this is because here's a reduction. Suppose you have an adversary that breaks the shadow, and we are reducing to security of one-way state generator. You get some copies of a one-way state generator state, you compute the shadow, which is efficient, remember, and we give the shadow to the adversary. If the adversary is able to find keys that break the shadow, break the puzzle, then the same keys can be used to break our one-way state generator. So it must be computationally hard to do. Otherwise, we would have a reduction breaking our one-way state generator.
For this, you need many copies of the state, right?
We
Not
need order
one
n
way.
copies, in fact. And this should not be surprising because single copy one-way state generators are known information theoretically, and in fact up to n by log n are known. So we need order n, and this is where that comes in. Now, one-way puzzles, we think that these are interesting in their own right because they model a quantum process that is sampling hard problems along with their solutions, which seems like an interesting complexity theoretical assumption. And you can think of them as being like a randomized variant of one-way functions, where for a single key k, there can be many possible puzzles, whereas for a function, there is the k maps to a single output. And we also show along the way, not in this presentation, but one-way puzzles are a necessary assumption for the hybrid cryptography setting. And the hybrid cryptography setting is a setting where parties are allowed to do quantum computation locally, but all their communication must be classical. So any type of, or all the types of cryptography that we could think of that you would do in a hybrid cryptography setting, all of those also imply one-way puzzles. So it is in some sense capturing some kind of minimality in the hybrid cryptography setting. And also one-way puzzles, because they have classical inputs and classical outputs, it can be easier to show separations using one-way puzzles because you don't need to care about having to break a quantum state. There's just a classical string and you find a classical inverse.
So Kabir, how do you even show this? Like one-way puzzles are necessary for hybrid cryptography?
Let's start with some, say, encryption scheme.
Yeah. You want to capture a fundamental primitive which captures every hybrid primitive.
Maybe this is exaggerating a little bit. I guess what we are saying is all the hybrid cryptography definitions that we came up with, they all imply one-way puzzles in a very simple manner, in the same sense that classical cryptography ends up implying one-way functions. It isn't very complicated. And it should be easy to see in the most case because there's always some classical string that is being hidden in some sense. Because your communication is classical, so the only thing you're dealing with is classical objects. The only slightly tricky case is for commitments, because anyway, like maybe for a different time. Yeah, so we think one-way puzzles are interesting in their own right. And apart from that, we show that one-way puzzles can be used to build EFI pairs and quantum commitments. And well, you might think that, oh, that's easy now because you have classical inputs, classical outputs, just apply the classical techniques, everything should work out. But there is a barrier here. And the barrier here is, consider just the construction from one-way functions, where you have some y, a one-way function, it has all these pre-images, we are going to hash the pre-image appended to the one-way function. In this case, for any given f of x value, for any given y, every pre-image is equally likely given y, which is to say, if we plot the distribution over pre-images for any given y, there'll be a lot of preimages which are simply not preimages. They'll all have probability 0. And then you will have some preimages which occur with like the same high probability. However, in the quantum setting, because these preimages are being generated by this quantum sampling algorithm, this generation algorithm, they're not simply being chosen uniformly at random. It could be that some preimages are more likely than others. In this case, the preimage distribution of this one-way object, given the output, different preimages could be more or less likely. The distribution could look arbitrary. It could be like spiky and weird and flat in some places, not flat in other places. And it turns out, for the Hill techniques to work, we crucially need this preimage distribution to be flat. And by flat, we mean that all of these points should have probabilities close to one another. So for a non-flat preimage distribution, the classical techniques don't work. And to fix this, we note that for any distribution that you look, arbitrarily distribution over preimages, the overall distribution may not be flat, but there is always some section of the distribution which is close to flat. And we call this single part of the distribution over which it is flat the good slice, because if we were only sampling from that good slice, our job would be done. It would be a lot easier. We have flatness, we can apply our techniques. And this section that is flat makes up a decent chunk of the probability mass of the distribution. So the idea is that we only want to consider keys that land up in this good slice, in this slice that is close to flat. So what we do, we make two changes. First is, we don't know what the number of preimages is, so we simply guess how many preimages they have. Simply guess the length of the hash and hope we get it right. This is a standard classical technique. I will not go into that. So the L is just some randomly sampled length. But the second thing we do, which is more interesting, is this final bit in our second distribution. Recall that our goal here was to get two distributions which are computationally indistinguishable, statistically far, and efficiently sampleable. So what we do here is the final bit in the second distribution. We say that we set it to be identical to the final bit in the first distribution unless the good event occurs, where I will tell you what the good event is. So if the good event does not occur, then these distributions are simply identical. However, condition on the good event occurring, we can start to analyze. And the good event is defined as our x just happens to be in the good slice that we want. If the x happens to be in the good slice and we guess the length of our hash correctly. If these two things don't happen, then distributions are identical, we don't care. However, we claim that the good event will happen with noticeable probability, so often enough. And when it does happen, condition on that case, we are in a world that is much similar to the classical setting. And then what we can then say is that these two distributions become computationally indistinguishable, statistically far, using hashing tricks. And so we get statistically far, computationally indistinguishable. There is still one problem here. And the problem is that sampling this bit B, it may not be efficient, because you are saying, okay, if your x just happens to be in the good slice, if you can check that this exact good event happened, then you're done. How do I know this good event happened? But do note one thing. The first distribution is still efficient. It is only the second distribution which is inefficient. And while we cannot say it is directly efficient, we can say something stronger than statistical distance, which is we can claim that the second distribution has more entropy than the first distribution. Intuitively, this is because exactly in the position where this gold-like Levin hash in the first distribution is some fixed value, we make our final bit in the second distribution a random value. So in some sense, it has more randomness, more entropy in the overall distribution. And this is a very high-level idea. This actually turns out to be non-trivial to show.
So classically there's this leakage simulation lemma, which says that if you have like you can basically fake the like this by an efficient function. Like right now it's not efficient, this bit B, but like the membership in the good set, you can kind of, like in order to fool an adversary, you can like run this what's called as a leakage simulator, which is efficient, but it's like it's going to just fake this value. I don't know if something like this works in the quantum landscape.
I would have to look into how it works. I have not tried it. Maybe it works. Maybe it would simplify the proof. But it is not required.
You got rid of this? You want these to be efficiently samplable,
yes.
right?
So we will get efficient samplability by doing some more things, and I will tell you what those things are. We are running out of time, so I'll quickly skip through it. Idea is the second distribution has more entropy than the first distribution, yet they are computationally indistinguishable. This is a property that in the classical setting has been studied. It is called pseudo-entropy. It's like pseudo-randomness, except instead of being indistinguishable from random, it is indistinguishable from some distribution which has more entropy. And then there are known techniques to go from pseudo-entropy to pseudo-randomness, which is I don't have much time, so I'll very quickly gloss over this. We have two distributions. One has more entropy, one has less entropy. There's some small gap between them. Yet they are computationally indistinguishable. We will take the product of each distribution, take the product states. So take the product distribution, sample from the same thing many times. They remain computationally indistinguishable. The effect is this large product distribution now has a lot more entropy instead of just slightly more entropy. So we have a lot of entropy here, a lot less entropy on the efficient side. This is still inefficient to sample, but we'll deal with that. And now because it has a lot of entropy, it has less entropy, we will apply something known as an entropy extractor, which takes a distribution with a lot of entropy and converts it to uniform randomness. So you apply the extractor, it extracts out all of that entropy, gives you a uniformly random string. And now a uniformly random string can be efficiently sampled. Recall again, we want efficiently sampleable two distributions, statistically far, computationally indistinguishable. Computational indistinguishability is maintained throughout this process. Now this becomes efficiently sampleable because it's just a uniform block. And they are statistically far because this distribution has much less entropy than this distribution. So it is in some sense pseudo-random instead of being actually random. So we have a pseudo-random distribution and a truly random distribution. And this is enough to get efficient, far, and indistinguishable.
So the left-hand side is determined by x. And
Kind of like given x, there's also the shadow process which adds some entropy, but we can take care of that.
And the right-hand side has an entropy come from B.
Yes.
Okay.
And although B was inefficient to sample, it was after we apply the hash, the whole inefficient object is indistinguishable from this, or statistically close to this uniformly sampled, efficiently generated string.
Okay.
These are not things I've come up with. This is just standard techniques. And there is one caveat here that we need to know exactly how much to hash. So there are more steps needed after this. And in fact, in the classical world, once we get non-uniform pseudo-randomness where we know exactly how to hash, there are techniques that let us get full pseudo-randomness, which is equivalent to EFI. In our world, in the quantum setting, those techniques don't work. We have to come up with some new techniques using flavor swaps for commitments, if you've heard of it. If not, don't worry about it. It's simple techniques. And the overall picture is we start with one-way state generators. We apply shadow tomography to get one-way puzzles. Then we do the good slice technique with some careful analysis of entropies to get quantum pseudo-entropy, which gives us quantum pseudo-randomness. And using some combiners, we can finally get EFIs. While in the classical setting, it is just one-way functions, pseudo-entropy, non-uniform pseudo-randomness to EFI. Anyway, the conclusion is we use one-way state generators to get this nice object called one-way puzzles, which are also implied by all or most hybrid cryptography. And we show that one-way puzzles can be used to build EFI pairs. And this leaves many nice open problems. Well, one is that can you use EFI pairs to get one-way state generators? We don't know. The other is, can you relax the requirement for pure state outputs? And there has been some recent work which is along this direction, trying to relax this pure state output requirement. They're claiming that they get EFI pairs from mixed state one-way state generators using analogous techniques, but you can see that yourself. The other open problems are whether we can use one-way state generators to get some form of quantum pseudorandomness. In the classical world, from one-way functions, we can get pseudorandom generators. Can we get the analogous object of pseudorandom state generators from one-way state generators? We don't know. And can we build hybrid cryptography from one-way puzzles themselves? There has been some work here as well, showing some kind of hierarchy, that there are some hybrid cryptography primitives that cannot be built from one-way puzzles. However, things like hybrid cryptography commitments, which are really one of the weaker objects, we still don't know whether we can build them from one-way puzzles or not. And that is all from my side. Thank you very much. If you have any questions, feel free to ask.
So here you need pure output because the shadow operation is.
Yes, the shadow tomography procedure requires pure state outputs. So if you could find a way to avoid going through classical strings, if you could do the slicing and the entropy arguments directly on quantum states, you would be able to do it, and that is the path that they follow.
And why there must be a flat size in the pre-image distribution?
Why it must be a flat size? Why there must be a flat size?
Yeah.
It follows from a pigeonhole kind of argument. What we want for our flat size is the most probable point and the least probable point. Their probabilities should differ by a factor of at most 2. So at a very high level, if you take the log of their probabilities, the logs will differ by an additive factor of 1. So, and the total range of probabilities, of the logs of probabilities, ranges from like 0 to n. And you have to fit all your probability mass in like log of probability ranges of 0 to n, so 0 to 1, 1 to 2, 2 to 3. Eventually, in one of these ranges, you will have enough probability mass, and that will be your flat size. It is a pigeonhole principle style argument. You can probably work it out fairly easily.
Okay. Any other question?
So this in the shadow tomography, the estimation that part is inefficient.
Yes.
And it is okay in the reduction because we only use the shadowing that part. And that red box, the estimation is never used in reduction.
I guess intuitively it's because the object we are building also has an efficient verification. So over there also we are reducing to something that we cannot ourselves verify. Okay.
The target we are reducing to.
The reduction does not need to run E. Only the challenger needs to run E when we are breaking one-way puzzles. So, and breaking, just the fact that it breaks one-way puzzles is good enough to get us break for one-way state generators. And we don't need to check ourselves whether it breaks it or not. The fact that verification is inefficient does lead to different kinds of problems, because for many constructions using, say, one-way functions, you do check whether the output is a valid pre-image or not. In some, for example, amplifying from weak one-way puzzles to strong one-way puzzles. Amplifying from weak one-way functions to strong one-way functions, it is crucial that you check whether a value is a correct pre-image or not. So those things don't work. You have to find other interesting ways around it.
Okay, let's thank the speaker again.